Professor Dr. Alfred Driessen was born in 1949 and studied physics and mathematics at the universities of Cologne, Bonn, and Amsterdam, completing his degree in 1972. He received his Ph.D. in 1982 with research on quantum solids and subsequently conducted postdoctoral work on hydrogen behavior in metals. His academic tenure at the University of Twente began in 1988, where he served as associate professor and later full professor in integrated optics, focusing on photonic devices and optical waveguides. Following his retirement in 2009, Professor Driessen was named Professor Emeritus and turned his attention on the philosophy of science, examining foundational questions at the intersection of science, metaphysics, and religion. He has lectured and published on the philosophical implications of modern physics and the dialogue between science and theological thought, contributing to broader conversations on the nature of reality and human understanding.
Okay, thank you very much. And thank you very much for the opportunity to share my ideas with your institute. It's about the novel on the foundation of quantum mechanics. And novel, I think I'm not so novel, but it's not the mainstream what I'm proposing. Therefore, in a certain sense, it is novel. And it's about the foundation of quantum mechanics. The content will be introduction, then I will go to philosophy, because for the foundation of quantum mechanics, you need to do philosophy. It is not sufficient just to do physics, because you need metaphysics, as Aristotle is telling you. And in the philosophical consideration, I will look mostly to the relation between the whole and its parts. And speaking about natural minima, etc., and then we will come to the quantum. Once we have done the philosophical discussion, we come to the examples from quantum mechanics, spin of an electron or double-slit experiment, and thereafter discussion conclusions. Now let's start. We are in the year of quantum mechanics 100-year anniversary. So it's very nice, 100 years. And Nature, the journal says it's an unfinished revolution. That's true. Revolution, that is for sure, because if you look for the application of quantum mechanics, it's incredible. The transistor, the integrated circuits, and facilitating AI. And have in mind that the standard computer has more than 1 billion transistors. So you see, it's really great breakthrough. And the light source is LED. We have the displays where you have about 1 million independent light sources on one just computer screen. And the quantum computers which are coming up and will be another revolution. And it's all due to quantum mechanics. And nevertheless, it's unfinished because the revolution, it's how to understand it. It's not known. We don't know. For example, we have here something very nice, easy experiment. You have light. I've worked quite a lot with light and photons, so for the example is for light. It's light coming in on a window, glass window. Part is reflected and one part is transmitted. How much is it? We have Fresnel's equations, it's 19th century. It's not so difficult. But if we come with a single photon, 1 for 1, and we ask ourselves, will it be reflected or will it be transmitted? Then we see that no law of physics provides an answer. That's crazy. Such a simple thing which we have everywhere in life, we don't have an answer. Because all our equations of science in quantum mechanics give only probabilities. And for a single photon, that doesn't help so much. Because then the single event is not possible to predict with quantum mechanics or physics in general. What's the problem there? Therefore, the previous speaker mentioned already that there was Einstein who had his problems with quantum mechanics, even when he started by the development of the quantum mechanics. He's writing later in 36, I also explain why, in my opinion, quantum theory does not seem suitable for providing a valuable foundation for physics. One runs into contradictions if one considers the quantum theoretical description a complete description of the individual physical system or process. Yes, the individual physical system process is very difficult to describe by quantum mechanics. It is impossible. And then so the question remains, what is happening here? Are we missing a law that we have to study further, that we get this law, or is that inherent to physics? That is impossible. Or that if it would be inherent, would mean that physics doesn't describe all reality. That's a reality which is outside the realm of physics. Or we are looking for hidden variable theories. But what Einstein is remarking there, you see in the previous experiment, is still valid. We don't have a law which predicts the individual physical system or process. Richard Feynman, a Nobel Prize laureate, he said, and theoretical physicist, he said, if you think you understand quantum mechanics, then you don't. And if I would dare to say I understand quantum mechanics, so I would say I don't understand it. So it's very difficult to support this thing. But we can ask us, is there a problem with our physics or with the philosophical framework we are using? Could it be possible that the weirdness of quantum mechanics is mostly due to the background, the framework we have when we think about nature? And I would like to a little bit to discuss this philosophical framework. Before doing that, I would like to mention an old paradox of Zeno of Elea that was formulated 2,500 years ago in Greek and by Zeno of Elea and discussed by Aristotle. I'm sorry that I don't mention Indian philosophers. I know there's quite some substantial work, but they are unknown to me. I'm a little bit biased from my European background, sorry. But here you see Achilles, who is, Zeno of Elea would like to demonstrate that change of movement is impossible. And he said, look, we have there Achilles running in competition with the trottoir. And the trottoir, of course, is quite slowly, so it gives him a little bit position ahead to go. So Achilles is running, when Achilles is getting that point, the trottoir said progress a little bit. And it's the next time the same. And you see the distance they were running was small and small, but he will never reach the trottoir. Of course, that's not true, but the Zeno would like to say, look, that we have movement is only appearance. If you really think, you can see that it's impossible to have movement. And then the solution, what we get normally and if you look at Wikipedia and otherwise, it's the mathematics. You have distance versus time, you plot it, you can see all the sections of the movement, and you can make a calculation that all the sections added up is a sum, an infinite sum, but the sum of this infinite sum is adding up to 1. So there in reality, Achilles will pass it to twice as you expected. But this is it true that we can just make a translation from the physical problem to the mathematical problem? That's the introduction. That's saying a little bit in which type of consideration we go. And now we come to the philosophical considerations. I don't know whether it's too much philosophy, but we just try to go through it. And the relation between the whole and its parts. You can have many different ways. Here I have the Lego paradigm. You know, the Lego bricks children are playing with, and there are also artists working with it, and they get the picture to the right side. And if you look nearby, all reality is nothing else than these small, tiny Lego bricks. So this is the solution the atomists already in the Greek area, Democritus was proposing. If they divide all, you come to very tiny parts, And the difference between the things we have is nothing else than the arrangements of these tiny parts. That's somewhat true, because if we divide anything, we end up with atoms, that's true. But that doesn't mean that if we build up, that we don't get different inputs, that there's something new happen. Now we come to Aristotle. I am a favorite of Aristotle, not about his physics. He was, of course, not correct in his physical, but his metaphysics and philosophy. And for him was, he considered always the whole. So it's a complete thing, the thing, and there are different names, the thing, a continuum. Continuum sense something which is continuum, something which has a unity, or something you can count. And then he distinguished that you have two types of continuum, the static, one that says things, and the fluid one that's movement or change, or even time. A movement is a fluid continuum. And what is very important is we have first to go to look for the whole, not to the parts. In the Lego bricks paradigm, we go first to the parts and make the whole out of it. Now, Aristotle is saying, no, you have to go to the whole, and then you have to look for the parts. What does it mean? First, we have to make another typical Aristotelian distinction. We know from Hamlet to be or not to be. That's a question. But for Aristotle, something new is coming. There's a third alternative between being and being not at all. That's a potential being. So to be or not to be, or potential being. And if you apply it to the continuum, then we would say, like Aristotle, the continuum is a whole, but there may be potentially parts. So that the parts exist, but not the full meaning as the whole. The whole, that is what it's important. The parts, it's a different level. And the properties of these potential parts is they are small in size, of course. The part has to be smaller than the whole, and they have the same characteristic as the whole. And there exists a natural minimum. That's it about the natural minimum. Natural here in the meaning of its belonging to its nature, to its characteristics, to its essence. And that we have to look a little bit more. But before doing, we need to introduce additional concepts, the concept of abstraction. And why? We need, because otherwise we cannot understand what we are thinking about and what's the role of mathematics. Because we have the individual item and that is, for example, a bird. I've plotted here some birds with different colors and forms and things. See, with size, all can be different. And we can form a concept of a bird. There is a concept of a bird that is an animal with feathers, with wings, etc. But we don't specify the color of the wings, the length of his the legs, etc. So it's already abstraction, because all the information which is in individual bird is not there in the concept of the bird. But the concept of a bird is not changing. So with concepts we can do something like science. With only individuals who can't do science. And then we can do a next abstraction that we relate it not anymore to the sense qualities. Here you, at the right side, you find a circle. Now you find a grass field of a farmer who had some fantasy, and he had cut his grass in the form of a circle with a nice triangle in between. And of course, the circle is, if you say you see a circle, but it doesn't matter whether it's grass or it's anything else. It's something that is round and it can be defined mathematically, but we see it there. And if you, in this example, contemplate only the circle, we have abstracted from the physical reality. We end up in geometry and we end up in mathematics. And of course, with mathematics, we can do many things, but it's an abstraction, of course. And then there's a third level of abstraction. That is the realm of metaphysics. It's the studies of the general properties and structure of beings. It's quite abstract what I'm saying. It's the general properties and structure of beings, of things, and the relation between beings. For example, causality is discussed in the metaphysics. By the way, metaphysics is not only for the Friday afternoon drink. You can use it really for trying to understand reality better. Because metaphysical question is, for example, is physics complete? What Einstein was asking himself is physics complete? Yes. And what is to be a cause? That is a metaphysical question. Is there causality from outside space or time? Is also a metaphysical question. You can't answer these questions not by dealing only with physics. You have to do more than that, because you are an abstract level which is beyond the physical level. Here I have put it once again in a certain order. You have reality. It's rich, it's complete, without any contradiction. Reality, by definition, is without any contradiction. And it includes the nature of all things, the nature, the characteristics, etc. of all things is there. So it's a complete thing. The concepts, so it's the first level of abstraction, includes in principle our reality, but not the individual nature of things. So it's not there. The individual nature you cannot find in the concepts, because the concepts are already abstracted from many, many things. For example, the birds, the concept of the bird, we don't know whether that bird in this moment is flying or not, because it's not an individual bird. Then the level of mathematics, does not include the nature of things, because like in the circle, the grass field, the quality of grass doesn't matter for the circle. It's just a form which is there. And it's not a complete description. We know by Gödel. Gödel is telling all formal systems have statements which are undecidable. That means they're incomplete. So we cannot make a description of reality in mathematics and saying, no, we can catch all the reality. No, we can only certain aspects of reality getting in mathematics. And then we come to metaphysics, includes all reality, but not the specific nature of things. So it's even more abstract as of all. But we need all these levels, or we have to work on all these 4 levels. Now we come back to the whole and its parts and going to Aristotle's view. For example, is there a low size limit for the potential parts? Now we have an iron rod. When I think we see it on the right side, the top thing, and we can make a mathematical representation. You can make out of it a elongated cylinder or just a line. This blue line is the lowest picture. And then, of course, you can cut it. If you make a mathematical representation, you can divide it as much as you like. If you took the half and then the half and then the half, you can continue. You will never end. But the potential parts are cylinders or lines with reduced length, but they have the same characteristics, and mathematically such a body is divisible in infinite. But in considering the nature, that's a physis in Greek, then the rod is divisible, yes, but there's a natural minimum, that is the iron atom. Because if you would divide further, it's possible to divide, then we get something which is definitely different from iron. We get protons, neutrons, and electrons. We cannot say that these are parts in strict sense of an iron bar. That is very important, that we have the mathematical representation. You can divide it as much as you like. It is working, because mathematics allows as many points in between as needed, and you will never get the ending. But physically, the physics does not allow division up to the infinite. There's a minimum, that's a natural minimum. Now we could take another example from we had the iron wire, no, the cow. Can divide a cow? For the Netherlands, very important. We have many cows everywhere in the Netherlands, and but the problem is the cow is not divisible into parts with the same characteristics, because even if you would divide only once, then we get 2 parts of a cadaver, not 2 parts of a living cow. And then we get as a natural minimum of division of a cow, that is the cow itself. That's, it seems to be very strange, but logical systems, the unity is so strong that you cannot divide, then you get something quite different. And that it's, you have to remember, we come now to the second type of continuum, that's the fluid continuum. The static continuum we just discussed is a unity, may have parts, the potential parts have the same characteristics as the whole, there's a natural minimum of the part size. But what about the movements? It's a fluid continuum. The fluid continuum is I would say a static continuum with a changing in time, in position or changing itself. And also time is a fluid continuum. And we have the same properties like in the static continuum. It is unity. We have first to look for the total movement. It may have parts, potentially it may have parts, but first these parts, if there are parts, they have the same characteristic as a whole. But there may be a natural minimum of the part size. And now you already discover a little bit where I'm going to. We're going to quantum mechanics, about the natural minimum of movement. First, once again, look for the Zeno's paradox. The movement of Achilles and the tortoise is a whole. There is in reality no infinite number of sections in the trajectory. You can do it in the mathematical description, but in reality, there are no infinite sections of movement. There's one movement. And Aristotle himself did not speak about the natural minimum of the potential parts, but I do an analogy with the static parts. And we have also to consider that modern physics considers granularity in space and time on the Planck scale. Even in modern physics tells you that the argumentation in the mathematical domain does not work because you cannot divide space and time indefinitely. There are very tiny time moments and space distances which we cannot go beyond that. But in Achilles, Aristotle is telling, without external force, Achilles will overtake the tortoise. And that means there's no paradox. The paradox is only if you make this imagination of the infinite trajectories, you make the division of it, but that's not reality. The first is the movement. The parts are only potentially. About the minima in the movement, there we have classically an example which is working quite nice, and it was also known to the people who established quantum theory. So there's a movement of a string. On the left side you find the Greek lyra, 2,000 years ago, a little bit more, and right is the natural frequency of guitar string. First harmonic, second harmonic, third harmonic, and in fact, the equation which lead to these are the same as we solve a particle and potential well. It's here we have also, it's a movement you can divide, but only discrete values, not indefinitely. Now we come to the examples from quantum mechanics and how we can relate these things with each others. And let's go. The spin of an electron. I think The spin is a tiny angular momentum of the rotating mass of the electron, and you get also magnetic moment out of it because the mass is also charged. And the crazy thing is the spin of an electron is either 1/2 or -1/2. And there's no subdivision possible. You don't find something with a quarter or 1, spin 1. You find particles with spin 1, but not electrons. And we see that the natural minimum of the movement of the electron is equal to the natural maximum of the movement. There's no subdivision possible. So it's one speed, and that means also there's no way of reducing the speed of this rotation. If it's a real rotation, nobody knows, because then but there's this movement, it's a fixed value only, and it's very precisely 1/2. And that we have to consider once again, there's movement which you can't change because it's not divisible anymore. Now we come to the next. Okay, we come to the second experiment, and where we get the same effect, similar, no, not the same, it's a similar thing which in our analysis. We have Thomas Young. About 200 years ago, he made his experiments. You have a source, you have a double slit, and after you see nice the diffraction pattern. And now we do this experience with photons, electrons, protons, atoms, molecules, doesn't matter. Everything can you do that it makes these interference patterns. Of course, the larger the particles are, the more difficult it is because you lose coherence. But with light it's very easy to do. And then people are trying to do the following. Here on the right side, you try to know where the photon is going. It's going through one slit or through the other slit. And the crazy thing is, we see at the screen, we see the distribution system of light we get when we measure there. And we do all this experiment with a single photon. That means that once this photon is sent, we wait a little bit and send the other one, and this way it is read the distribution at the screen. If we block the slit, one of the two splits, we don't get interference. If these two slits are open, we get the interference we expect. We see it on the right side where we get this interference pattern. And it's crazy. If we would like to know where the photon is going, we destroy the interference. What is going on there? And we have this probability distribution at the projection screen. And it can be calculated with high precision for photons, for protons, for all kinds of things. What you do, it's namely the square of the wave function. And as we had with the reflection surface, for a single event, there's no prediction possible. Only where we have zero probability, so of course never a photon will come. But there is a little bit of red color, there you have, there's a probability that the photon will end. The collapse of the wave function occurs at the final point of the movement of the single quantum particle. And what happens, the collapse of wave function, that means that the probability is then set to 0 to all other screen points. We never measure half a photon here and half a photon there. No, it's only one photon at a certain position. And if we go to Aristotelian terms, we can say the potential trajectory of the moving particle has been actualized. We have a potential thing, we make it actual, a special thing. And that's ending in the final point. And then a question remains, who or what is actualizing the trajectory of the particle? We have it seen before. Maybe an unknown law of physics, or otherwise one has to accept the incompleteness of physics. That was Einstein didn't say incompleteness of physics, he says incompleteness of quantum mechanics, but we don't have another theory which could do so, and we have reasons to assume that there is no other theory which could fill this incompleteness. Heisenberg was mentioned in the previous talk, and he was stating, it's a quotation. I think it's interesting to use it because he's speaking over the Aristotelian potential probability, which the third alternative Aristotle already considers. He's saying, however, the probability wave of Bohr, Kramers, Slater meant more than that. It meant a tendency for something. It was a quantitative version of the old concept of potential in Aristotelian philosophy. Introduce something standing in the middle between the idea of an event and the actual event. A strange kind of physical reality just in the middle between possibility and reality. So you see these people were aware of what Heisenberg was saying there. Of course, this is written in 58, so 25 years later than or 30 years later than quantum mechanics was established, but I assume that he knew already before that. If we could look now for the double-slit experiment with the Aristotelian view, we have to consider the movement from the source to the detector as a whole. Like any movement, it is a whole. And then we can ask ourselves, is a division possible? And then we come to the conclusion, a mathematical description, perhaps, in reality, one has to ask nature. That's the characteristics of a photon. And the quantum world, the division of movement results in discrete steps, the quanta. And the natural minimum of division is often the complete movement. We have seen it already with the spin electron, but also the photon, that you cannot divide the trajectory of a photon. You're changing, yes, you can, but you cannot divide it. That means if you would go to divide the movement of the photon in this double-slit experiment, that you put something before the slit of one, then you divide the trajectory, and then the movement has changed. The character of the movement has changed, and you will see no interference. And that is the reason why certain things you cannot change. There's this minimum, this natural minimum of movement. You can do nothing in that. Now I'll come, yes, it's for discussion and conclusions. We have gone through quite a lot of things, but I would like to make certain things more clear. I have here a comment of Pascal Jordan. He is one of the founding fathers of the quantum theory. And he's quoting Leibniz, Natura non facit saltus, nature does not make jumps. And what he's saying, the idea of continuity, which attained its mathematical form in differential calculus, is important for the clear understanding of motive processes. We also want to make it clear immediately that this continuity of natural events, natura non facit saltus, was already evident in the elementary fact that it was possible to speak of a definite trajectory of a moving body. A body cannot reach one place from another by jerks, suddenly disappearing here, emerging there. It must describe a continuous, connected path between the two. And then he asks himself, why is that necessary? Why can a body not suddenly disappear here and emerge there? That's we have to get used to it. That's a question. He himself asked him this question, but why is it necessary? We don't know, because it's necessary if we have this idea nature does not make jumps. But nature may make jumps, why not? And then so that we had, so for example, if you look at the double slit experiment, we're looking for the trajectory of the photon. No, the photon disappears at the source and it's up in the detector, but it's in between. We cannot look in detail. Another comment, which is from Sommerfeld, also one, let's see, it's a generation before the quantum mechanics part, has several PhD students who made a Nobel Prize winner. He's writing, when on occasions I spoke about a new conditioned causality, it was mathematically founded. For it appears that we have to calculate the emission by a formula which initial and final condition of the atom enters equally and symmetrically. By the way, this is not entirely new. Aristotle considered, besides the efficient cause, also the final cause, as also Leibniz did. I show you below this formula. I don't want you to calculate with this. I only would like to show that in this formula, we find the final state and initial state symmetrically. Both contribute to the transition probability. And that it's important that the characteristic of a trajectory is determined by the initial and by the final state. And this can be indifferent in times with a large amount of difference of time. And if the movement is a whole, that is the statement of Aristotle, then the initial and the final points of the movement are decisive. In case of quantum particles, like the photon, the natural meaning of the vision is a whole. No division is possible. And that means that the final point, the trajectory, the path, determines what is going on all of the tracks of the photon. And the final point of a movement can be set long after the initial point. See Wheeler's delayed choice proposal, I will show later. And these are experimentally confirmed in 2007. It's very important. The photon's trajectory is not fixed at the initial point, the source. Of course, the source determines what is coming out, but it's not the only one. What is a delayed choice experiment? We have here a double slit experiment. Now I've put the source far away from the slit and the detector, and you can put the shutter in the figure below. It's a lower split, it's blocked. You can choose a position after the photon has emerged from the source. And the crazy thing is that it has still influence. Still, in the case of no shutter before one of the slits, you get interference, and one shutter is there, then you get the single slit experiment. You can, that means even if source does not know which position would it be, later it follows the trajectory. And this once again, because the trajectory is final trajectory is only fixed once the final destination point is determined. Wheeler had a very nice thought experiment in 1978, and he said, imagine a photon source far away from a quasar, and whose image has been split by a galaxy, which acts as a gravitational lens. Okay, that means you have to go very deep in the universe to see it, but you can see it. And then at the final state can be an interference setup, and then the photon will follow both paths from both sides of the gravitational lens, or you just look with a telescope and you see either the photon come from one side or the other side. The crazy thing is that the delayed choice is made after a billion of years. And that it's very difficult to imagine that the trajectory of the photon is only fixed after a billion years. But it confirms that the trajectory of the photon is a whole, is a complete thing. You cannot make the parts out of it. And of course, this experiment here we see galaxies hasn't been confirmed, but it has done in a laboratory, and the distance is large enough that it's real change after the light has left the photon source, that you make the setup of an interferometer or not. And Wheeler is getting correct. I will come to the conclusions. The what I'm saying, at least for me, probably for you, hopefully also for you also, that Aristotelian metaphysics provides an intriguing framework for the foundation of quantum mechanics. Things which are weird probably are not anymore so weird if you have this view on the reality. The occurrence of natural minima in things, such as the static continua, motivates the acceptance of minima in movements, the fluent continua. Aristotle provides a road to understand the role of the wave function in quantum mechanics by allowing a third alternative, potential being, besides being and not being at all. And then last thing, accepting the incomplete character of physics, which I think is quite straightforward. Nevertheless, we made enormous progress in the fundamental and applied science. And you can say nevertheless, but I would just, when we accept the incomplete character of physics, we can make progress in physics. That means we have to look also on the metaphysical level, who are the other actors acting in our experiments, where do they come from, and not only look from physics. At last, I would like to acknowledge many of the ideas of what I've presented is from a book from Peter Hoonen. It's a physicist and theologian, and has written books in Dutch and in Italian, so in Latin, so they're not easily readable. But in about more than 50 years ago, but it was very valuable to me. I also would like to thank the Bhaktivedanta Institute for the opportunity to share these results at the summer schools. Thank you very much for your attention.
Thank you, Professor Driessen.
So thank you so much, sir. So my question is, there was a point about continuity and like why nature cannot make discrete jumps. But I think like in neuroscience, we have seen that often the brain fills in the gaps and we have our experience appears continuous. But could that be the reason why continuity and classical physics seem so intuitive to us, but nature could fundamentally be discrete?
Yes, I don't know why for us we like to have it is continuous, but discrete, I think it's true. And but I think also what happens that we are biased a little bit from the 19th century background philosophy, which is it's like that the whole universe is like a mechanical thing with gears, etc., and everybody is moving the other, and that does not work in quantum mechanics. Because reality is not a machine with interacting parts. It's much more complex.
Like metaphysically, do we have any reason to believe like continuity should be preferred over discreteness, like fundamentally?
No, I don't think so. I don't think so. We have, of course, in mathematics, we have to use continuously because otherwise our differential equation will not work. But normally, no, it's. I wouldn't say that's necessary. And for me, also the example of music. Music, we are used to discrete values of movement. And if you have continuous sound in melody, we would consider very rare music. We wouldn't like it.
Do you believe there can be a theory beyond quantum mechanics, which is not a hidden variable theory, that is fully deterministic? Because even if the outcomes of our measurements are random, they could be governed by some deterministic laws.
That could be. That it's, But first, I would like to say, to make this decision whether that theory is possible, that you're going already to metaphysics. In the physical domain, you can't answer that theory, that idea. Of course, you can, so let's see, how can I explain? See, in science, you say the mathematics is the language of science. But you know, in mathematics, you cannot generate a random number. It's impossible. If it's a computer, you can't generate a random number, not with mathematics. And with mathematics, you can't decide whether something is random or not. It's impossible. And that means to deal with these questions, you have to go to a different level. Mathematics is not suitable for that. And that means also physics, which is using the mathematics for these laws, can never decide whether it's deterministic or not, or what is the... No, you have to go further. You're welcome. Thank you very much.
Be a part of this.